the PV term is in fact a measure of energy. Because if you think about it, pressure is force divided by area. Well, force, we'll just keep as force. What is area? Area is length squared. What is volume? Well, volume is length cubed. And that means that pressure is in units of force times length. But what is force times distance? Well, that's work or energy. So that's then, PV is force times length, and that equals an energy term. So just to say, pressure is force over area, pressure times volume is force over area times a volume term, and that means that PV is force times length, which is an energy or work term. And so basically, when we get PV over T equals NK, we can rewrite that as PV equals NKT, and PV is an energy term, so NKT had better be an energy term. And what that really means is that since N is the total number of atoms, that very roughly speaking, KT is the energy per atom. Now, in fact, of course, it won't be the energy of every single atom, since the atoms are constantly bumping into one another and changing and sharing momentum and kinetic energy. So, in fact, of course, there will be a distribution of energies, but the average energy will be, per atom, will be KT. And so on average we can say that the energy of each atom is KT. Now let's get to the nub of the problem, black body radiation. What is a black body? Well, essentially a black body could be a box. And it's a box which does not reflect electromagnetic radiation. That means that any electromagnetic radiation that comes along is absorbed. And generally that means you have to paint a box black, and then it won't reflect the radiation, it will absorb it. A black body does not reflect electromagnetic radiation, it absorbs it. Now, it can't keep on absorbing it, because if it did, then the energy in those waves would heat up the internal parts of the box, and you would get into a situation where that box got hotter and hotter, and the room outside got colder and colder. And that would be a violation of the second law of thermodynamics, which essentially says that heat cannot of itself pass from one body to a hotter body. So what happens is that once that box gets into what's called thermal equilibrium with the room outside, which for all practical purposes means once it's at the same temperature, then as much radiation from electromagnetic waves that goes in will also cause radiation to come out. And so the black body box becomes a radiator. Energy goes in the form of electromagnetic radiation, and it comes out. Now you might wonder whether perhaps the radiation simply goes in and comes out. But in the days of classical physics, this is before quantum mechanics was known, scientists were at least aware of molecules and atoms. Just exactly what they were, they didn't know. But they knew they existed, and they knew that electromagnetic radiation interacted with atoms and molecules. In the minds of the scientists, what they did was that when an electromagnetic wave hit an atom, it caused it to oscillate or vibrate, rather like a spring that is oscillating backwards and forwards. And in doing so, it was generating electromagnetic radiation. We now know, of course, that what is actually happening is that the atom, which consists of a small nucleus with orbiting electrons, we now know that what happens is that the photon comes in, transfers its energy to the electron, and promotes the electron to a higher energy orbit. But then that electron wants to get back to a lower energy state, and so it falls back down again at a later time, and in doing so it emits a photon of energy, which will exactly equal the energy between the outer orbit and the inner orbit. But that's what we know now. That wasn't known to the scientists at the time. However, people like James Clerk Maxwell, who had done so much to bring electricity and magnetism together, knew that a charged particle which was accelerated would generate an electromagnetic wave. Indeed, that's the way that television pictures are produced. There is a television aerial, and by accelerating electrons up and down, by having a alternating voltage on either end of the aerial, causes the electrons to accelerate up and down, and as they accelerate they produce electromagnetic radiation, usually at the UHF level, and that's called a carrier wave, and the television signal is contained within that carrier wave. And when it gets to your television, the television simply strips off the carrier wave and leaves the signal, which then becomes your television picture. And that principle was known in the time of James Clerk Maxwell, well before quantum mechanics was developed. So what was assumed was that you had a black body, that radiation came in the form of electromagnetic waves, that it interacted with an atom in the gas in the middle of the black body, or indeed with the walls of the black body, set that atom into some kind of vibration, and that vibration would generate the electromagnetic radiation which would come out. But what would be the wavelength of that electromagnetic radiation? Well, as far as scientists at the time were concerned, it could be any wavelength it liked. It would just depend on what oscillations the atoms were doing, and that could be anything. So if you were to plot the intensity of that radiation against the wavelength, you might expect that you get a straight line. Intensity, incidentally, is just a measure of power, and power is essentially energy divided by time. So intensity is an energy measure. And you might think that since the atoms are capable of developing any wavelength electromagnetic radiation, that the intensity of all that radiation would be the same. Experimentally, however, it had been found that if you plotted the intensity of the radiation that you got against the wavelength, you got a graph that looked a bit like this. This would be for a very high temperature. If the temperature were lower, it would look like this. And if the temperature were lower still, it would look like this. And the things to notice about this graph is that as the temperature goes down, the peak at wavelength goes to the right. In other words, the wavelength increases as the temperature decreases. And secondly, you'll notice that in all cases the graph goes up and down on either side of the maximum. This, for example, could be the visible light region of the electromagnetic spectrum, whereas this might be the infrared region of the electromagnetic spectrum. And that accords with our everyday experience. For example, when you put on an electric fire, initially, when the temperature is not very hot, you might just feel the heat coming out of the fire, and that's infrared. But if you wait for a while, the filament will get much hotter, and consequently the wavelength will decrease, and that means you get into the visible light region, which is why after a while you will actually see the filament glow orange and then orangey yellow.